Okay. All right, so just a recap about significant figures. So we see two measuring devices here, and the measuring device is what's determining the number of significant figures that we're reporting in our data. So here I can look at this and I can make a guess of that last number. I could say 5.4, I could say 5.5, 5.3 maybe even, okay? But it's just a guess, right? I'm just guessing what that number, that last digit is. And your scale in the laboratory is going to do the same thing. So when you go in there, if you have lab today, you go in there and you're measuring something on the scale, that last digit on the scale is going up and down, up and down, up and down, because it's a guess. You have to guess that last digit. It's never going to stop. I mean, it might kind of stabilize a little bit, but it's always going to constantly be going up and down, because the scale's guessing and you're just going to have to guess, because that's the last significant digit on the scale also. So here I can guess that 5.4. Here I have to guess more. I have to guess farther into my number, because I have more precision in this instrument. So here I know for sure it's 5.3. That's what I know for sure. But between 5.3 and 5.4, I'm not sure, so I have to guess what it is. 5.36. I make a guess. That's my last significant digit. Okay? So that's the idea behind significant digits. They're just guessed numbers, like we talked about last time. And how do I know if what I'm reporting or what I'm looking at is a significant digit or not? Well, all digits are significant if they're non-zero digits. If a 0 digit has value to it, then it is not significant. Value not significant. No value, well, significant. Okay? So you have to consider whether it has value or whether it doesn't have any value. Okay, and they're going to go through some rules here. But really, it's those two things. That's what you need to know. Whether it has value or not. Does it have value? Does it not have value? But if you want to look over these, and if this is an easier way for you to learn it, fine. Okay? So information bearing digits, that just means non-zero digits, okay, are significant. The measuring device used to determine the number of significant figures a measurement has, okay, it determines that. The amount of uncertainty, that's the significant digits, is showing the uncertainty in the value. Okay? Okay, here's the rules. All non-zero digits are significant. In a number containing a decimal point, all zeros at the end of the number are significant, significant, not significant. Okay? All zeros at the beginning of the number are not significant if we're talking about the decimal. Okay? So, but what you really need to remember, if you remember what I've told you, then, I mean, all this verbiage here doesn't really, you don't need to learn it or memorize it, because you know this. Does this 0 have value? No. So is it significant? Yes. Do these zeros have value? Yes. Are they significant? No. That's all you need to know. Okay? If you know that, you'll get it right every time. In a number with no decimal points, all zeros at the end of the number are not significant. Once again, see this 0? Does it have value? Yes. Is it significant? No. This is a sandwiched 0, so we know it's significant because it's between non-zero digits. Okay. It's independent of the position of the decimal point. Zeros located between non-zero digits are significant. Zeros at the end of the number are significant if the number contains a decimal point. Okay? Significant? Yes. But all you have to ask, does it have value? Does that 0 there have value? 4.7, 4.70 doesn't the same number. If I put that number in my calculator, it doesn't change the answer, right? It's the same. So that means that this 0 is significant because it has no value. I write it. Why? Why do I write it if it has no value? To show the precision of the instrument I use to collect that data. That's the only reason, right? I have to maintain the integrity of the instrument I used in reporting that in my data. That's the only reason I put it there. Otherwise, I would leave it off. Okay? Trailing zeros are insignificant if the number does not contain a decimal. Okay, once again, do they have value? 100 versus 1. Do these zeros have value to them? Yes. Are they significant? No. If they have value, they are not significant digits. Okay? Now, if I put a decimal there, that changes things. Okay? So 100 decimal. That means that decimal forces those zeros to become significant. Okay? The reason I write that decimal is to show that that's part of the significant digits. Okay? So that's just something you're going to have to remember. The decimal forces those zeros to become significant. Okay? Zeros to the left of the first non-zero integer are not significant. Okay, once again, do they have value? Yes. So are they significant? No. Good. Okay? All right. So here's a few questions. They're showing you the answers here. 478, that's 3 significant digits. 6.01, 3 significant digits. 0.825, 3. This 0 has value. It is not significant. 1, 2 significant digits. Okay? This is written in scientific notation. Anytime you write something in scientific notation, you always write it with the exact number of significant digits that you have in the number. So it's easy. If it's written in scientific notation, I simply count the digits. 1, 2, 3, 4. There's 4 significant digits. Okay? Because you have to write scientific notation with all the significant digits. Okay? That's one of the rules of writing scientific notation. How many are in this one? 1. These are placeholders. They have value. So they're not significant. Okay? So there is 1 significant digit in that number. Okay? All right. Any questions so far? Do I need to go over any of that? Yes, ma'am.
So the 0 to the left of the decimal, we don't count that, right?
So I'm trying to figure out left over here, this one.
Yeah.
Okay. So no, you don't need to count that digit because you could have it there or not, and it's not really changing anything. Yeah. So it still follows that rule. It's not significant. Okay. Any other questions? Okay. Now, there are rules we need to follow when we are adding or subtracting significant digits. And addition or subtraction of significant digits occurs when we take the numbers and we line them up by their decimal place. Okay? So whatever numbers we're going to add or subtract, we basically line them up by their decimal place, and then we cut it off, the answer that we get, we cut off to the decimal place with the least number of decimal places, to the number with the least number of decimal places. Okay? So 1 significant figure after the decimal place here, so that's where we cut it off. This has 3. Okay, so this has 1, so I'm going to go to that 1. So I'm going to round that 0.4, the 90, I'm going to round it to 90.4. I'm going to drop the 3 too. Okay? Does that mean that every time you do an addition subtraction question, you have to write it out like this and line it up? No. If I was just given that in a question, 332 plus 1.1. Without lining these up, can you tell how many digits I'm going to keep after the decimal? Yeah, I don't have to line it up, right? I don't have to do that. I can look right there, and I can see this has 3, this has 1. So my answer needs to be to how many decimal places? 1. Okay? So I don't have to do that, okay? Because I can see here where the answer is going to go to. Okay? 3.70 minus 2.9133. I can see I'm going to take 2 decimal places, right? So if it wasn't lined up like this, I would already know I'm going to take those 2 decimal places. So I'm going to drop the last 2 digits, and I'm going to round to 70.79. Okay? 0.79. That's how I'm going to add or subtract significant digits. Multiplication and division is easier because all I have to do is I have to find the number in the calculation that is to the least, that has the least number of significant digits in it, and that's what I report my answer in. So here I have 3 significant digits. Here I have 1, 2, 3, 4, 5. This is my answer. What do I report my answer in? Well, I report it in 3 significant digits. So my answer will be 16.5. Even though this is to 2 decimal places, my answer is only to 3 significant digits. 16.5. Okay? So with multiplication and division, I only report to I report my answer to the same number of significant digits as the data in the question that was to the least number, which probably didn't make any sense to you because that was confusing. Okay, so this has more, this has the least. I use that number of significant digits in my answer. Okay, so 1, 2, 3, 1, 2, 3. Once again, division. 2 significant digits. 1, 2, 3, 4, 5. So my answer needs to be reported in how many significant digits? 2. To 2 significant digits. So I round this to 2 sig figs, 0.061. Okay, so that's addition and subtraction, multiplication, and division. All right. And make sure if you have a mixed question, you're following the order of operation. Okay. I'm going to do the addition and subtraction first within the brackets, and then I'll do the multiplication and division at the end. Okay. And I'm following these rules as well. Okay, exact numbers. So we'll run into numbers sometimes that we consider exact numbers that are a result of counting instead of the result of measuring something with a measuring device. Okay? So if you count something, then there's no uncertainty in how much you have. If I go and I count beakers in a cupboard, and there's 10 of them, I know exactly that there's 10 beakers, right? There's no uncertainty in that data. That's an exact number. So how many significant digits would the number 10 have if it wasn't an exact number? It would only have 1. But in this case, because there is no guessing to it, that number has an infinite amount of significance to it. Okay, So if I use the number 10, so if I say there's 60.05 times my 10 beakers, whatever that would be, okay? And I want to report this to the least number of significant digits, how many digits would I report my answer to? 4. Because this 10 has an infinite number of significant digits because it's the number of beakers that I counted. That's an exact number. This one has the uncertainty in it. So this one only has 4 significant digits. This has an infinite number of significant digits. Okay? So I'm going to take this, 6.64, 6.68, 6.70. I'm going to find the average of it. There's 3 data points. So I divide it by 3. That number 3 is not just one significant digit. How many significant digits does this 3 have? Infinite number of significant digits because it's a result of counting. 1, 2, 3 data points. That's exact. Okay? So there's no uncertainty in that number 3. So when I take the average here and I divide by 3, I do not report my answer to 7. I report it to 1, 2, 3 significant digits. Okay? Because this is my data. Okay, so let's carry out the following. Let's just first look at these, and let me ask you, in A, how many decimal places am I going to go to? 1. There you go. You don't have to line it up. You just have to look at that and say, which one has the least number of decimal places? This one. How many decimal places are there? There are 1. So my answer will have 1 decimal place. So I will add those 2 numbers together, and then I will round it to the first decimal place. Okay? B, how many decimal places am I going to keep? 2. Okay? Good. So it's not too bad, right? So I just go to here. How many significant digits am I going to keep in C? 3. This has 3. This has 1, 2, 3, 4, 5. So I need to go to I need to report my answer in only 3 significant digits because that is the least number of significant digits in the question. This has 3. This has 5. So I will report my answer in 3. How about the D? How about D? Okay. 3. Why? How many significant digits are here? 3. How many in the other one?
3.
Good. They both have 3. So I would report my answer to 3 significant digits. Okay, so here I have 2.64 times 10 to the third plus 3.27 times 10 to the second. 2 what? Okay, so this has the least number of decimal places, right? So it might help to write these out if you can't visualize it. Great job, those that you could. Okay, so 0.00264 and 0.0327. Okay, so now I can see, 2 decimal places. That's where I need to go to. I need to go to those 2 decimal places.
Why would it be that way?
A negative? I'm sorry? You're adding those 2 numbers together. We're going to add these together.
No, he was talking about the exponent.
Oh, I see. You're right. I don't know what I'm doing. Woo. Stuck on negatives. 2640 3 27. Okay, so then where am I going to go on this one? Well, I guess instead of the number of significant digits, where am I going to cut it off when I add these together? Yeah, right there, right? That's where I'm going to go. Okay, so I'll report my answer yes to 3 significant digits. Okay, but that's where I'm going to cut it off. All right, because this one goes farther in significant digits than this one. So you always cut it off to the one that has, I guess, the first stopping point. Whereas if it was decimals, it would be the same idea. Okay? Thank you for clarifying that. Okay.
Hold on. Can you clarify that one more time? So, because it's addition, though, is it 2 or 3 decimal places? Is it decimal places or significant digits that we're looking at?
We're looking at where is the last significant digit in either one of these numbers, and we're going to stop the rounding at that digit. So remember, we're lining these up by decimal place, right? This is the decimal place.
Right.
Okay? And so I line them up by decimal place. This 0 right here is not significant, right? This 7 is significant.
Right.
Okay? So that means that this place right here, all right, the hundreds, right? That's where I need to cut it off. Because if I go farther, this won't this won't hold true if I go this far, because this data doesn't have significance all the way to there. Okay? But this one does, this one doesn't. So if I want to report my answer of these two numbers added together, it needs to be to this many digits, because this one doesn't go that far. So I have to cut it off.
The decimal point would make the 0 significant.
Well, there isn't one there. I just wrote it there to show you that there's a significant. That's where I'm lining it up. But there isn't a decimal there, right? We don't have a decimal place right there. If I did, I wouldn't. The only reason I would write the decimal there is if I didn't write it in scientific notation, to show the significance of this. Okay? You see how there's no 0 here? If I had a 0 there, that's different. That would be a significant digit. Then I would need to report all of these. Okay? If that was a significant 0, I would have to report all those. Okay? Are we okay with that? Any more questions? No? Okay. All right. Okay, so accuracy and precision. So here, what is accuracy? Accuracy is hitting that value, the true value. So you're in the laboratory and you're carrying out experiments, and you know what the true value should be, and you're trying to replicate that. Do you get there? That's accuracy. Are you able to replicate that? That's your accuracy. Okay? That true value. Precision is the ability to carry out an experiment and get the same answer again and again and again and again. It might not be the true answer, but you're getting the same answer. So you're being precise in how you're doing it. Maybe not accurate, but precise. So here, the bullseye, I hit the target with precision. I continually hit the bullseye. That's accuracy and precision. I don't hit the bullseye, but I hit in the same place consistently. That's precision. Maybe not accuracy, but precision. This one has neither accuracy nor precision. Okay, it's just all over the place. Okay, so a data set like this would mean nonsense to you, basically. You have nothing to go on. You can't go on anything. It's just all over the place. This I can at least go on. Okay, I'm getting some sort of result over and over again. So maybe I need to correct something, or maybe it's actually telling me something different. Okay, I can learn from something. Or here, this is what I'm trying to accomplish, and I am. All right. Okay, so in chemistry, we're going to do a lot of dimensional analysis. And that dimensional analysis allows us to determine whether we're doing the calculations correctly and setting everything up correctly. Okay? And there's a very simple method to follow when we're doing this type of calculations or conversions, we can call it. Okay? So you always start with whatever you're given. Okay? So the way that I'm going to perform this dimensional analysis is I start with what I'm given. And I usually like to set it up kind of in this format. Okay? So I start with what I'm given. And I'm going to multiply that by the thing I'm trying to get to, the unit I'm trying to get to. Okay? And then I'm going to divide by the unit I was given, I started with. That's called my conversion factor. That's converting from something that I was given to the other thing. And if you have a conversion factor that can do that, then I simply have to multiply that conversion factor by the given unit, and I will be able to successfully convert it from one thing to another thing. Okay? So that's what we're going to be trying to accomplish. A person's average daily intake of glucose is 0.0833 pounds. What is the mass? What is this mass in milligrams? So, what is my given here? .0833 pounds, right? That's my given. That's what I'm starting with. I want to convert it from pounds to what? To grams, and then to milligrams. That's right. Okay? So that's the process. If I know the process, then I'm just simply going to set it up across the top. I'm going to go from pounds to what first? To grams, because they gave me that, right? Pounds to grams is right here. I'm going to do that. I'm going to go from pounds to grams. And then, because the metric system is so amazing, I can easily go from the grams to the milligrams. Okay? And they don't have to give me some strange conversion like 1 to every 453.6. Okay? So, that's the process. I set it up like this. Pounds to grams to milligrams. I know the process I want to follow. What unit do I have to put down here to accomplish this conversion? I have to put pounds down there because I have to get rid of, the pounds, right? They have to cancel out. What unit's going to go here? Grams. I have to get rid of the grams to go from grams to milligrams. Okay? So one thing you should realize is that if I was setting it up like this, okay? This is wrong because why? What are the units of this calculation right here? The answer.
Grams squared over, pounds squared over grams.
Pounds squared over grams. That's not what I want, right? I don't want that. I want to get rid of the pounds and be left with the grams. So I have to flip it this way. Is there ever a situation when I'd use this conversion factor in this way? What would I be starting with if I was using it in the way that I have it written here? I would need to start with grams. Now I can convert it to pounds. Okay? I get rid of my grams. It's the same numbers, the same conversion factor. I'm just using it in the opposite way because I'm starting with the other thing, right? But the numbers don't change. It's still 453.6 grams for every 1 pound. That's what they told me the conversion for that is. They said there's 453.6 grams in every 1 pound. So I can use it in that way, or I could use it in this way. 1 pound has 453.6 grams. Okay? All right. Now, milligrams to gram conversion. Milli, yes. Milli is something I want you to learn. I want you to know what that prefix means. If I have a milligram, how many milligrams are in 1 gram? That's how I should say it. There's 1,000. Milli means 1,000. There's 1,000 milligrams in every 1 gram. Now, if it was something other than milli, like pico or femta, I wouldn't expect you to know that. I would give you the conversion for that, okay? But if it's a milligram, I want you to know that means 1,000 milligrams in 1 gram, okay? All right. So this is how I would set up that conversion. My units all cancel, and I'm left with milligrams. And so I know I'm doing it right. This is what we call dimensional analysis. Dimensional analysis is the process of putting your units there first before you put your numbers in and making sure everything is set up correctly. Because once your units are all in there, I know the numbers to put. I know which numbers to put there once I have the units correctly placed. Okay? It really helps. So now I can calculate this. Okay? And this one's easy because I'm just multiplying everything. Because look at the bottom. It's just ones. So I don't have to divide by anything. 0.0833 times 453.6 times 1,000. Okay? And that will give me my answer. How would I perform this calculation?
0.0833 divided by.
That's right. This one is 0.833 times 1, which you don't have to do, divided by 453.6. Okay? That you always multiply across the top and just divide by everything on the bottom. Okay? What if these were your bottom numbers? Now how would I perform the calculation?
Multiply the top, divide by the 31 and 21.
Okay, good. That's the best way, I think, to do it. So there's lots of ways that you can do it. Some of you, you're going to multiply across the top, get an answer. You're going to multiply across the bottom, get an answer. You're going to take that top number, divide by that bottom number. That's fine. But I don't recommend it because there's too many steps there where you're going to maybe make a mistake because you're writing numbers down and then you're dividing them and you're not keeping all that calculation in your calculator. Okay? What I recommend is going 0.0833 times 53.6 times 1,000 divided by 31 divided by 21. Do it all in one calculation, one step. Not one step, but one calculation. And your calculator is going to keep all that information, and it's going to give you the exact answer. Okay? I think I've found that is the best way for students to perform these types of calculations. Okay? And that's going to become really a process we're going to follow a lot, especially in Chapter 4. I think it's Chapter 4, if I'm not mistaken. Okay? Chapter 4, when we get into stoichiometry, you're going to be doing that kind of stuff. Lots of conversions and multiplications across the top and divisions on the bottom. And if you set it up correctly, but you calculate the answer wrong, you know, that sucks really bad, right? So make sure that you're doing it in the most simple way that you can so that you're not making calculation mistakes, because they will hurt you. It will count against you. Okay? Okay, an average adult has 5.2 liters of blood. What is the volume of blood in meters cubed? 1 liter equals 1,000 centimeters cubed, and 1 centimeter equals 1 times 10 to the negative 2 meters. Okay, fine. All right, so 5.2 liters of blood. 5.2 liters, okay, equals how many centimeters cubed? Well, okay, sorry. I guess I was expecting you to do that in your head, but let's just go ahead and set it up. Okay, so what's the conversion factor here? What is the conversion? What's the process? That's what I should ask. What is the process we're going to follow here along the top? Liters to centimeters cubed. Okay? Once I find my centimeters cubed, I think I'm going to take a break from the conversions, and I'm going to change that centimeter cubed into centimeters. Okay? So, how would I do that? How do I change a cube into its unit? That's right. I take the cube root of it. I'll take the cube root, bring it back down to centimeters, and then I will start over with however many centimeters I have, and I will convert it from centimeters to meters. And then to find my answer in meters cubed, what do? It's in meters. I cube it. I don't take the cube root again, I just cube it back. So meters cubed will give me my answer in. So the reason that you're not going to find this, we're not going to do this a whole lot, okay, this kind of thing. But the purpose behind this exercise is to show you that you cannot go from units of cube or square and just directly convert to something else. You have to bring it down to its units where you're using where you have the conversion factors. It needs to be in those type of units for you to do the conversions, and then you can go back up. Okay, so that's the idea of what we're doing here. Okay, find your centimeters cubed. Take the cube root of that equals centimeters cubed. Take the cube root of it, and when you find your centimeters, convert it to meters, and then you'll be able to go back to your meters cubed by cubing it again. Okay, this equals my meters, and then I'm going to cube that, and that'll be my answer. Okay, that's the idea behind that. Okay, liquid nitrogen is obtained from liquefied air and is used to prepare frozen goods and in low temperature research. Yes, it is. The density of the liquid at its boiling point is 0.808 grams per centimeter cubed. Convert the density to units of kilograms per meter cubed. Okay, so this is a good example of what we were just talking about. So we're going to take 0.808 grams per centimeter cubed. Okay, and I'm actually going to write it like this, grams per centimeters cubed. Okay, now we want to go to units of kilograms per meter cubed. So I need to convert both the grams and the centimeters cubed. I need to change both of those units. So the grams I'm going to convert to what? Kilograms from the grams, right? And then the centimeters cubed, I'm going to convert to what? Well, actually, what I need to do first is once I find this number, okay, I need to change it from centimeters cubed to kilograms per centimeter. After I find this answer right here is going to be in units of kilograms per centimeters cubed, right? So I need to change that. I need to change that, okay, to instead kilograms per centimeter. Okay, so once I have it in units of kilograms per centimeter, then I can, let's see, where am I? Okay, then I can go, I'm sorry. Then I can go to meters from the centimeters. Sorry, writing that wrong. To meters from the centimeters. Now, why did I write it on top here? And why did I write it kind of backwards from how we've been doing it? That's right, because the centimeters needs to cancel, and since they're on the bottom, I'm going from centimeters to meters. So if it's the unit on the bottom I'm changing, I need to follow that process along the bottom, okay, instead of on the top, okay? And then I can, I'll be able to get there, all right? Kilograms per meters, and then okay, so these are our units that we would use, okay? Okay, so let's try a few of these examples. A physician orders 15 milligrams per kilogram of a drug for a patient who weighs 80 kilograms. How many milligrams of this drug should the patient receive? Okay, so here we're going to, what information are we given? What are we starting with?
Given the mass of the drug, right?
Okay, 15, we're given a patient, okay, so how many milligrams? We want to find out the milligrams of this drug the patient should receive, right? And we're starting with the 80 kilograms, and that's the individual. That's how much they weigh. We want to know how much of the drug we're supposed to give them, and you're supposed to give them 15 milligrams for every kilogram the patient weighs, right? So we're going to set up that conversion here. The conversion factor is milligrams for every kilogram, and it's 15 milligrams for every 1 kilogram. So 80 times 15. What do we get? Where's your calculators? Let's do it.
1,200.
What is it?
1,200.
Oops, I'm sorry. That was 10,000. 1,200 milligrams. Whoops. Yeah. Yes. Okay. 1,200 milligrams of the drug. That's how much I should give them. Okay? Or 1.2 grams. Okay. The prescriber orders clonazepam, or PAM, clonazepam, 0.05 milligrams per kilogram daily in 3 divided doses for a patient who weighs 60 kilograms. If each tablet contains 1 milligram, how many tablets of this anticonvulsant drug should the patient receive per day? How many tablets would the patient receive per dose? Okay. So the patient weighs 60 kilograms, right? Okay. So how many tablets would the patient receive per dose? So let's see. So 0.05 milligrams per kilogram daily in 3 divided doses for a patient who weighs 60 kilograms. each tablet contains 1 milligram. Okay, so what information are we trying to extract from here? What are we trying? So we know how many tablets would the patient receive per dose. Okay, and each tablet is 1 milligram. So what's my first conversion I want to accomplish here? What do I want to figure out? I'm probably going to have to do this in more than one step. I think we want to figure out how many milligrams I need to give an individual in a day, basically. So 0.05 milligrams per kilogram daily. Okay, so how many? What I want to know is how many milligrams is that in one day? That's the first thing I want to know. So what do I do? What's my first setup here?
60.
Good. 0.005 milligrams per kilogram. Okay, that's the first step. Now I know how many milligrams I need to give them overall in one day, but I need to divide that dose up by what? By 3. In 3 divided doses for a patient. Okay? So they need to take this 3 times. 3 times per day, for every 1 day, right? That's not what I want. That's how, oh yeah, this is milligrams per kilogram, which is basically per day also. That's how much we're going to give them in 1 day, okay? So I need to divide by 3 doses for every 1 day. So I can write day down here as another unit per day. Okay? All right. So that's where we're at. Okay? How am I going to finish this off? How many tablets would the patient receive per dose? Okay, so it says that each tablet contains 1 milligram. Okay, so I want to know how many tablets. So I need to go 1 tablet for every 1 milligram. So that's just a 1-to-1 conversion right there, right? Because the milligrams here will cancel and I'll be left with the number of tablets. Okay, so my units, and I'm left with tablets per dose. How many tablets per dose? That's where I want to get. Okay, so what do we get here? 60 times 0.05 divided by 3. 60 times 0.05 divided by 3.
3 milligrams a day, 1 tablet per dose.
That's, yeah, so 3, right? If it's 3 tablets. Okay. Okay. The prescriber ordered heparin, 2,000 units every 12 hours. The label on the multi-dose vial reads 10,000 units per milliliter. How many milliliters will you administer to the patient? Okay, so we want to know ultimately the number of milliliters to the patient. So this many units every 12 hours, and it's 10,000 units per milliliter. Okay, I want to know how many milliliters. Okay, so this is how much 2,000 units every 12 hours. Okay, so I want to convert that 2,000 units. Okay, into milliliters from units. So there's 10,000 units for every 1 milliliter. Okay, so you can already see that 2,000 units is going to be less than a milliliter, right? I don't know if they finished that question. So maybe they mean daily, because they're saying every 12 hours you need to give that much. And they're saying how many milliliters will you administer to the patient every 12 hours or daily? And I think they mean daily. How many? And there's 24 hours in a day, right? So we're just going to have to multiply that by 2. So 2,000 divided by 10 would be the amount that we would give every 12 hours. Okay? So that's that conversion. And then if it was daily, you would multiply that by 2.
So would it be 0.4 milliliters per day?
If it was 0.2 milliliters every 12 hours, then it would be 0.4 every day. Yeah. Yes. That's right. Okay. All right. How many? So I know this seems like we're just keep doing these, but they're really important. It's really important that you guys really get this down, because this is one of the things that determines your success in here, is whether you can really perform these types of dimensional analysis and conversion questions, and because we're going to work with it a lot, okay? And that's a lot of the type of math that we'll be doing in here. How many seconds there are in 1 week? Okay, so seconds, we have 1 week. And it just says set up the dimensional analysis. Okay, so we're going to go from week to what?
Days.
To days. Hours. Minutes. To seconds. Right? And so what unit? And basically, and this is how it always works, you just drop your units. Just drop your units. So weeks, days, hours, minutes. Okay? And then everything cancels. And once you have everything set up how you should, you can easily see where do I need to put my numbers. I don't have to try to guess. Am I multiplying by 60 or am I dividing by 60? I don't have to guess. I see it exactly how it's supposed to be. Okay? All right. Okay. So it ends up being a big number. I'm just multiplying across the top on that one. Everything else is on the bottom is just 1. Okay. Miles per hour to feet per second. So 65.0 miles per hour. Okay. And I want to go to feet per second. So what's the first conversion I'm going to use here? Okay, miles to feet. What's the second conversion I want to do? Hours to minutes. Okay, to minutes to seconds. Right? And then I'll be left with feet per second. So miles to feet, hours to minutes to seconds. So what unit goes on the bottom here? What unit goes right here on top? Good. Hours. Okay? Because the hours need to cancel just like the miles canceled here. What goes on the top here? Minutes. There you go. And I'm left with feet per second. So does anybody know the conversion for miles to feet? It's a runner over there. 5,200 what? 80? 5,280 feet for every 1 mile. Good. Okay. Okay, so how would I perform this calculation? This is a good example. How am I going to enter it in my calculator? Multiply across the top, 65.0 times 5,280 divided by 60 divided by 60. That's how I'm going to do it. Okay, that's the best way. What are you guys finding?
95.33.
Okay, how many significant figures should I report my answer? I started with 3, and it's just basically conversion factors here, so I'm just going to report my answer to 2. Okay. All right, so 95.3 feet per minute. I started with 3 significant figures, and it was multiplying it by conversion factors. And exact numbers. I mean, this feet per mile, there might be some uncertainty in it. But still, that would give me the 65.0. But these ones, that's a result of counting, essentially, right? There's exactly 60 minutes in an hour, right? So we'll just consider those unlimited significant digits. Okay. Is that a consensus, by the way? Did everybody else get that too? 95.3? Okay, good. Oh my God. Okay, I don't think we need to waste our time on that. Okay, let's go ahead and let's do chapter. Let's start into chapter 2 before we get out of here. Okay, enough with chapter 1, right? I'm tired of it. Okay. I like chapter 2 much better. Chapter 1's kind of boring. Okay. So chapter 2. We're going to talk more about atoms and molecules and ions and that kind of stuff. And naming. All right. So we're going to talk about a few scientists. And these scientists, they came up with kind of the basis of what an atom is. So Dalton Dalton was the first scientist who actually carried out experiments. And through his experiments, he began to develop postulates about what an atom was. So he wanted to understand, because the definition of matter, of matter, is that it's anything that has mass and occupies space, right? So if it has mass and it occupies space, it's matter. What is it made of? It's made of something. And so Dalton wanted to know, what is that matter made up of? And there was this idea of the atom, that matter consisted of atoms, but he was the first scientist who kind of showed experimental data to kind of, I'm not going to say prove it, but to establish this idea of the atom. And so here, he began, through his experiments, he began to develop these postulates. And his postulates were so good that even today, they hold true. Okay, even though he didn't have a full understanding of what an atom was, or that sort of stuff, he's just a pioneer in this. He developed these postulates that hold true even today. And so his first one is that matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. So if I have copper wire, that copper wire is made up of copper atoms. And it can undergo chemical change if you react it with something else. So that's kind of where he's getting at with his first postulate. Okay? Or here's a penny. Okay? And we see it's made up of copper, that penny. Okay? Well, you have to get an old penny, by the way. And they weigh more. They're actually copper. Today they're not the same. They're a mixture of stuff. So, because we became cheaper. So, okay. Now his second postulate, an element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. Okay? So he's saying that this copper has only copper atoms. And that that mass is characteristic of that element. So I look here and I find the mass of copper, right? 63.546. That mass defines this as copper. A copper atom has an atomic mass of 63.546 atomic mass units. Okay? That's what he's saying. That's pretty good. It's pretty good for his time. Now, this postulate is no longer entirely true, and we'll talk about why. But for what he understood, working with undergoing chemical reactions with his samples that he had, this is correct. So if we don't consider nuclear chemistry, the chemistry of the nucleus, okay, then this is great. Okay, if we're just reacting stuff or decomposing them, then that's true, because that's what we're working with. We're working with a sample of copper, and that's what we're reacting or decomposing, and that's what we're getting. Okay, and we're going to see why this doesn't hold true 100% anymore, but how it is still pretty true if you're just looking at it at the molecular level instead, or the atomic level instead of the nuclear level. Okay, atoms of one element differ in properties from atoms of all other elements. Okay, so one type of atom is different than another type. Oxygen is different than nitrogen. Okay, or than fluorine. All right, yeah, they're different. They react different. Their masses are different. Their properties are different. Okay, postulate 4. A compound consists of atoms of two or more elements combined in small whole number ratios in a given compound. That's true. When I react something together, here the copper is reacting with the oxygen. Okay, and it forms copper 2 oxide. It has exact ratios. There's exactly so many coppers. There's exactly a 1-to-1 ratio actually here. 1 copper. So the formula here would be copper CuO, copper 2 oxide. Okay? So I have 1 copper, I have 1 oxygen. That's the ratio, right? 1 oxygen for every 1 copper. That's my ratio. It's whole number ratios. H2O. I have exactly 2 hydrogens for every 1 oxygen. I don't have half an oxygen, right? Or 1.5 hydrogens. I have exactly 2 hydrogens and 1 oxygen. Whole number ratios, because these are entire atoms that are coming together, and you're not going to get half an atom to come together, right? So we have to have whole number ratios. So these are his postulates, and he was right about that. Okay? Number 5. Atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those present before the change. Okay? So when I carry out a chemical reaction, I don't destroy the thing that underwent that chemical reaction. It doesn't go away. It's still there. It just got rearranged. How do I know that? Well, because here I have copper and oxygen. I react them. I form copper 2 oxide. The copper and the oxygen are still there. They're just now chemically bound together. I didn't create them. I didn't destroy them. I just rearranged the molecules. How could I verify that? Because if I decompose the copper 2 oxide, what does it become? It goes back into copper and oxygen. They're still there. So just like H2 plus O2 forming H2O. The hydrogen and oxygen weren't destroyed. They were just rearranged. And I can verify that because if I decompose it, it will go back to H2 plus O2. They're still there. Hydrogen and oxygen are still there. That's what he was experimenting with. This is what he's discovering. He's reacting stuff, then he's decomposing it. He's pulling out the same stuff. This is exciting stuff to him. You guys are like, oh, that's boring, Mr. Fenner. Who cares? Okay? But you know, he was pretty excited about that. So, all right. Okay, so those are his postulates. All right, mostly still true today, and without one exception, and that is simply due to the fact that we understand more now about the masses of these elements. If I have a sample of oxygen that weighs 15.9994 grams, that is not because one oxygen atom has a mass of 15.994. No, one oxygen might have a mass of 16. Another oxygen might have a mass of 17. And the average of those is what we get there. Okay? It's the average of those. It's the average. This right here, this mass, is a sample of oxygen or a sample of copper. It's a sample of it. So within that sample, I might have copper 63 and copper 64. Well, I will, actually. I shouldn't say might. I would. I would have those different coppers, and their percentages would then, if you average them, their weighted average of those would come up with those numbers. Okay? And that's why Dalton's postulate is no longer completely true, because of isotopes. And we'll talk about isotopes next time. We'll see you guys. Have a good day.